What happens when AI can reason, use tools, and safely interact with programmable money? In this course, you'll build practical Web3 agents that read on-chain data, prepare transactions, monitor events, and finish with a deployed capstone project. Think of the course as a build path. We'll start with agent fundamentals, add blockchain capabilities, then connect wallets, DeFi, events, and multi-agent workflows before hardening everything for secure deployment. The sequence is deliberate. Agents first need to reason clearly and use tools reliably. From there, they can read blockchain data and prepare actions with the right context. Only then do we introduce wallets, approvals, and contract execution. Autonomy comes gradually because financial actions are high impact. Throughout the course, safety, logging, policy checks, and compliance are part of the architecture, not extras added at the end. Use this course actively. If you're newer, start at the beginning and make time for blockchain and safety basics. If you're intermediate, go deeper on the modules tied to your project while still refreshing the foundations. If you're advanced, treat the lessons as a reference and scrutinize the security choices. Build as you learn, keep notes, test in safe environments, and ask questions before real funds are involved. A chatbot is mainly a conversation partner. You ask, it answers. An agent goes further. It pursues a goal, chooses tools, remembers context, plans steps, executes actions, and checks results. That difference matters in Web3, where actions may touch wallets, smart contracts, payments, or live data. Before AI operates in those environments, we need to understand how language becomes controlled, accountable action. Here's the distinction in simpler terms. A chatbot is conversation first. It takes a message and returns a helpful response. An agent is goal first. It decides what needs to happen, calls tools, checks the outcome, and continues until the job is done, or it reaches a boundary. In Web3, that boundary is critical because tool use can affect wallets, contracts, RPCs, and real assets. An agent works as a loop, not a single model call. The model and prompt interpret the goal and constraints. The planner turns that goal into steps, while memory tracks what has already happened. Tools and an executor let the agent act outside the chat, such as calling APIs or reading blockchain data. Then the environment returns results, evaluation checks progress and safety, and the agent decides what to do next. You can also think of an agent as operating inside 3 layers. The goal defines what success looks like. The instructions shape how it should behave, which tools to use, what tone to take, and how to make choices. The boundaries define the hard edges. No private keys, approval before spending, testnet before mainnet, and clear stop conditions. In blockchain, these boundaries matter because a vague rule can become an irreversible transaction, lost funds, or a security incident. Tools are the bridge between reasoning and real systems. A user asks for something. The agent selects a controlled function, like get wallet balance or simulate transaction, and the tool runs with defined inputs. It then returns a structured result. The agent should verify that result before responding or taking another step. In financial workflows, this control is essential. Agents should not improvise transactions. They should use well-designed tools with clear outputs, permissions, and failure handling. Planning turns an agent from a chat responder into a task executor. It starts with a broad goal, breaks it into concrete steps, and executes one step at a time. After each action, the agent checks the result and revises if needed, instead of blindly continuing. In Web3, this loop needs an extra safeguard. Before preparing any transaction, the agent should pause for risk review, permission checks, and user confirmation. Memory helps an agent stay continuous instead of starting over at every step. Short-term memory keeps the current task coherent. Long-term memory can store preferences, approved workflows, or known addresses. Tool result memory can prevent repeated calls to slow or costly services, which matters on-chain. But memory is also a risk surface. Private keys, seed phrases, raw secrets, and sensitive approvals should not be casually stored. Good agent design remembers useful context while tightly limiting anything that could create irreversible damage. Autonomy is not a switch you flip from off to on. The safest approach is to move through levels. First, an agent recommends. Then it prepares work for a human to approve. Next, it can execute inside clear limits, such as budget, scope, or risk rules. At the highest level, it operates continuously, but only with monitoring, audit trails, and emergency stops. More autonomy can create more value, but it also requires stronger guardrails and clearer accountability. A reliable agent does not act once and hope for the best. It observes the environment by checking data, logs, APIs, and blockchain state. It executes through controlled, approved interfaces. Then it evaluates the result against the goal and safety rules. If something is wrong, the agent should not improvise blindly. It should retry with limits, ask for human approval, or stop. This loop is what turns automation into dependable operation. On-chain agents require special care because their actions can become real financial events. If an agent receives a prompt like "approve unlimited token spending," the unsafe path is direct execution. One click could create a permanent approval that drains a wallet later. The safe path is slower by design. Simulate the transaction, explain the effect, require human confirmation, and enforce spending limits. Never expose keys to the model, and treat every prompt as untrusted until verified. You now have the core distinction. Agents don't just chat. They pursue goals through reasoning, tools, memory, planning, execution, and evaluation. As autonomy increases, safety must increase with it through approvals, limits, logs, and emergency stops. Next, we'll make this practical with tool calling and function execution.